Here we go. Thank you for coming. SF-BISH. SF-BISH is Bay Area signal hackers. Yeah, so if you send me an email, I will send you the presentation slides, and or you can just send me an email and say hi. It's all good. So I just also want to say it's okay, to talk in this room. You got microphones everywhere on the ceiling, and internet people will hear you. But don't worry, if you say anything, I will not. I will edit it out if it's not appropriate. And so yes, not only that we can hear you, but I will be recording also. And so let you know. And keep going. So this is SF-BISH. So Bay Area signal hackers, and so we've been around for a long time, and these companies been sponsoring before. I personally know that because I used to work in nodes and KNOWLES. I used to work in that company like more than 10 years ago, and that's when I first attended the SF-BISH meeting, and that was like it's really more than 10 years ago. So. And now I'm working for MathWorks, and we are sponsoring it. So what we are is a bunch of people that's really interested in signal processing, and we get together and have fun. We can exchange ideas, talk about signal processing, and that's the main thing. We can socialize and connect. I like these local meetings because we can actually play audio and we can hear things. And if someone has a demo, we can set it up and people can see it. And so it's not like a IEEE conference paper where it's just presentation. You don't get a feel of what's going on. So that's what I'm trying to go for. And in fact. Well, okay, these are the organizers, the original organizers, and so I'm going to suggest maybe next time I'm going to have more demonstration. Maybe open up in the other room, have a row of demonstration booths, so that like other people who is interested, they can come and present. I mean, showcase their stuff. I think that might be interesting. So whatever it takes to get more people to come. I'm really grateful that you are here all today. So I always want new ideas to expand. For example, I think the food, maybe I can do something about that. Maybe I can get maybe a cooking contest and get this gourmet companies. But anyway, it's all depending on how many people show up. If I have more and more people, then I can talk to my boss, and then hopefully we can sponsor more, and then we can have better and better stuff, food and things. So yeah, so these are the original organizers, and I'm fairly new. So okay, so we have a lot of presence. We have the meetup group link. We have a YouTube channel. If you're not sure, last year. I had hosted the same event, and we recorded the video and was posted out on the YouTube channel. So if you're interested, you can go to the YouTube channel and you can view other presentations. And I think that's really interesting. We have LinkedIn, we have other links, and so please help spread the word. And we want to make it more interesting and more people can come. All right, let's get to the main topic. So this is the agenda for tonight. And so basically, we will have two presentations. Then I managed to slip in a 10 minutes break so that people can get something to eat. And then after that, we have two more presentations. The last one is it's just for fun, and it's a very short presentation, but I will play sound, and we can see how much you can hear and stuff like that. And on that note, actually, I plan on maybe presenting nonlinearity perception, maybe next time, and we will have maybe a live demo of echo canceller, active noise cancellation, maybe. So it's all coming up. So keep an eye out. Okay, so this is the first topic: modeling acoustic devices and enclosures. So this is mainly for acoustic. So first, I want to show like modeling acoustic devices, meaning that that includes a loudspeaker or maybe a microphone, and like some people they build up, for example, a echo cancellation system, and then they don't include the loudspeaker part. And notice that the loudspeaker section here, I don't know if you can see it, it is actually in analog domain, while the rest of the system is in discrete time domain. So the other system, maybe I can quickly go through. On the top left, I will play a sound. This is echo cancellation. So maybe for internet gadgets, like these Alexa devices, it's playing music, and then you can say, Alexa, and then the device would immediately catch your keyword. And how does it do it? Because every time, whenever you place the sound out, the sound picked up by the microphone has to be canceled out, and such that the new keyword come in, it can be captured. So that's what's going on here. This is the same mock-up. So the music here is upper left. It's being played, going through the D to A converter, get into the loudspeaker, and get back into A to D, going to the discrete time domain, and that's when I put in the room effect and also merge in the speech command in one, and then go into a simple RMS adaptation, trying to catch remove the transmitted sound. And so this is a quick demo showing that why do people want to simulate loudspeaker together with a signal processing algorithm. And that's the thing is, if I have the loudspeaker in here, including the loudspeaker nonlinearities, then the residual noise level after the RMS will be much higher. And so this is actually a scenario where these big companies, they have to do to improve their product. What they can do is put in a nonlinear cancellation to help out in this echo cancellation scenario. So this, the important point here is that I have a mix of discrete time and continuous time system. Continuous time system, we'll talk about Laplace transform, we'll talk about differential equation. That's what you need to solve to get the system response. So it's a bit different. And later on, we'll see that the loudspeaker model actually is a multi-physics domain. So it has electrical, mechanical, and acoustic domain. So another motivation of mixing signal processing and acoustics in analog is this, maybe as an example. In this active loudspeaker system, you can actually put in a neural network controller. And this simulation allows you, this is a Simulink simulation, that allows you to put in a neural network together with an analog system, a loudspeaker. And this, with the protection scheme on, now you can crank up the gain and trying to increase the loudness of your speaker to the maximum without worrying that it's going to crack or damage the system. So it is needed. I would say all the active speakers, they would have a protection scheme inside. So that's the motivation. And this is kind of the agenda that I will be talking about tonight. I have shown you a loudspeaker model of DSP applications. Now, this is followed by a brief introduction to what is the acoustic library that I've been using and how does it come about. And after that, I will show you an earbud example, speaker model that's modeling, for example, the AirPod in your ears. And after that, I think I've mentioned that these are all models, but how do you get the parameters? And we have adaptation methods, not adaptation, but we have the optimization toolbox that can help. And yeah, this is getting more a little bit into modeling and tuning a loudspeaker enclosure. Now we have a way to simulate an analog system. It is straightforward and fun actually to tune a loudspeaker enclosure. You know, I mean, I was building my own loudspeaker box before, and then, but now with a way to simulate the whole thing, you can actually just do it in the simulation mode first, and it saves a lot of time and it's fun to do. And the last item is like the acoustic library allows you to simulate sound, propagate, going through certain structures. And I will show you quickly how that was done. So this is the acoustic library that I've been advertising. So this has been released on the free exchange site MATLAB Central. You go in there, you can download this library, and there are like all these components that you can put it on the canvas and connect and play with. So I want to talk a little bit about what's inside of these components. So let's start with this one. This is a micro speaker. So, all right. So when we talk about a loudspeaker, this is a loudspeaker driver. You can see that there is the electric side that we put in the wires connected to the loudspeaker. Then from the wire, it will have the coil. The coil will have a magnetic field, and this magnetic field will move the whole cone and the diaphragm front and back. And this movement, it's a mechanical movement. This movement will push the air in the front and creating sound out. And that movement obviously is affected by the enclosure, the box behind. Whole loudspeaker modeling side that I'm talking about. Now, in the model, the loudspeaker is essentially being modeled with all these lumped elements. You can see the blue section here is in the electric domain. Well, I model it. I even include like inductors, resistors, and then this will be followed by a simulation in the mechanical domain, where it's being simulated in say mass, spring, and damper model. And then in the end, there's the acoustic domain. And the acoustic domain, we have like inertance and compliance that looks like an inductor and capacitor. So this is a multi-physics simulation. So let's step back a little bit. So now this whole system, I have discrete time, I have continuous time. In the continuous time, I have multiple physics. And so this multiple physics simulation side is a subset that we call SimScape under Simulink. So in Simulink, we want to simulate physical elements. It's under a subset called SimScape. So some people were saying, what is SimScape? They got confused. And so like all this whole model can be written like a code and collapse into one component. And this is what comes about by with the acoustic library. We have a micro speaker component. So this slide is the same as this slide. So Now we have one component, and now we can use this component to build more complicated systems, like this one. This is the earbud speaker example, where you have the micro speaker followed by the earbud, and then a model of the ear canal, followed by the eardrum simulator. So all this is simulated, and we can measure sound pressure and see what is the response. And you can see that I have included the leakage, meaning that there's a hole back in the outside here that's leaking back out. So all this you can simulate it. So what's the advantage of simulating the whole thing? So now you can tune your design. You can adjust to see, what if I make the hole, back hole a little bit bigger? Or what if I put a denser screen in the front? What is the net effect? What is the effect of this frequency response? So now you can tune these things, you can adjust it, and that's another reason why people want to simulate acoustics in using lumped elements. And basically, it's just one thing is it's a one-dimension simulation. It's simple, it's easy, and it's not like there are these three-dimensional tools that you have to put in a lot of details on the materials, and you need a CAD, you need all these to simulate something simple. This is intended to be something simple that you can screen out 95% of your errors or tunings fairly quickly before you go into like a really detailed model, if you still need to. Yeah, so this is my simple example for simulating a loudspeaker box. And this box has one ported output. So you can see that in the simulation, I simply use the driver component. And at the back of the speaker, I connect it to a box. In the box, there's a port output that I pull out. And then I have two air loading attached to it before I measure the sound pressure. So for those who are interested, this air loading is based on Beraneck's model, which is frequency dependent. It's like, the impedance change according to the sound frequency. So it's 1 kilohertz tone or 5 kilohertz, it's different. So anyway, so this is a simple example. I have another example, it's the fourth order bandpass box. Now this one is interesting. It's got a closed enclosure in the back, and in the front there's another chamber and open a port out. Now in this case, you can see that it's intuitive now to simulate this system. In the back, I put a box. In the front, I put in a port and measure the output. So this is hopefully it's an easy way for people to move forward and try out new things. I have put out 9 examples out in the MATLAB Central. Well, actually, it's being reviewed right now, and it should be out by next week. So I think like if you send me an email when you ask for the slides, at that time it's probably out. And if it's out, I will make this a hyperlink instead, so you can take a look. Yeah, so this particular one here, this is a radiator. It's not a driver, so there's no electric component connected to it. So it's interesting. So now it's a brief explanation about the model. So whenever there is an enclosure, like a box, a chamber, then we will model it as compliance. So there will be a capacitor, or it looks like a capacitor. It's a compliance. If there is air mass being pushed, and I will be modeling it as inertance, so like an inductor. And if there's a leakage of air leaking out, then it's a resistor. So this is a basic lumped element approach, and it's a popular way to do simple simulations. And using this kind of system, you can actually build out a real model, like a different complicated model, and you can then simulate it. Now, building it up is one thing, but after you know, let's say this is a compliance and all that, but how do you get the parameters, proper parameters for your model? So that's what we will talk about next. Now, there are two ideas here. Number one, when you buy a loudspeaker driver, the spec actually comes with these really small parameters. And then, or some of them are actually physical parameters you can directly apply. But if they are really small parameters and stuff like that, you wonder, how do you translate it from that to the model parameters? And I have another calculator I have released on, it's almost released again, on MATLAB Central. I call it the really small calculator. So over here, you can put the really small parameters here, and the corresponding electrical or mechanical values will be reflected. Or if I change, for example, this resistor RE, then the really small will change, and the estimated resonance frequency will change. So it's a calculator back and forth. Shown here, there are three graphs. These are the nonlinearities related to the loudspeaker. There's the B field, there's L field, and the K compliance field. Polynomials, people can get it when you measure it, for example, using a clipper measurement, and you get polynomials. And all these you can apply into our loudspeaker model. Allows you to say whether you want to include these nonlinearities or you just want it to be linear, and it's all flexible. Now, there will come to a time where you have some measurements and you want to put it in the model, but you don't know what is the values to actually match your actual measurements. So in those cases, well, we are MATLAB, so we have response optimizer. It's under the optimization toolbox that will help you to say adaptively find out the proper parameters. And on the other side, if you have a design and you want to optimize, for example, your frequency response, and so your degree of freedom, maybe you only want to change the weight of the coil, for example. And for those, you can also use optimization toolbox to try to optimize and find out what's the best value to achieve your criteria. Now, I want to quickly talk a little bit about tuning a loudspeaker box. This is a simple loudspeaker box. And if I don't have a port open, then it's a closed box. And when I have a closed box, you can feel that it might be harder for the driver to push air because it's sealed off. And so the suggested resonance frequency for the driver will be pushed higher up when you have a closed box. And so meaning that the low frequency sound might suffer. You might lose a little bit on that. So to get it back, you can open a port, and the effect of that would be like this spring model here. So you have sound going out in the front, and you also have sound going out in this port, and in between you have a spring. You can see that at certain frequency, those two will be pushing in the same direction. And that's what we want to do. We want to tune the port so that the air is pushing out in the same phase. You can see if it's a different phase, then it might cancel some of the sound intensity out. So it's kind of defeating the purpose. So that's what I meant by tuning. You need to adjust the dimension of to achieve what you want to get to. And so this is the simulation showing that when I have a closed box and as the volume is getting smaller, I'm actually pushing up the resonance frequency up. So this yellow line up. You can actually easily see it in the simulation. By putting a port in, I have created a new mode, and therefore you can see the net frequency response can be pulled lower. So that's the whole idea. Okay, so similar to solving electromagnetic structures, but there is a popular finite difference time domain method. But we can apply a similar method in acoustics, meaning that we can simulate the sound going through a tube, or and simulate it by assuming it as a concatenation of a basic acoustic element. And each of these acoustic elements is modeled by like this T model with inertance and one compliance. So this way of simulation, that's what I call like an FDTD approach. But we have already a component that's doing something equivalent. So we have a component, let's say, going through this tube-like structure. You can specify how many segments you want to build, and you can then simulate it and get the response back from this tube. Like what is the resonance frequency of this tube? How many volts you get? Stuff like that. Now by tube, notice that it's not confined to be a cylindrical tube. It could be a rectangular type. So, and okay, so losses. There are two main losses, and one is the viscous loss that's come about by the back and forth motion of the acoustic particles, especially closer to the wall. And the other one is the oscillation pressure going up and down, so minute temperature change while it's flowing through, and that will also create a loss. And these two losses are frequency dependent. So 1 kilohertz will not see the same loss as 5 kilohertz. And these losses we have already included in the model. So you can check, say, enable it, and then it will be turned on. And we have these components, for example, already included this. The details of this simulation, it's done in time domain. It's been done according to this paper by Dr. Thompson. Dr. Thompson has been helping us out with this acoustic library. And he's the one who actually presented to us last year for SF-BISH this time. And he had this model released. This is the clarinet model. So it simulates basically sound going through this tube with different finger holes you can play with, and it will simulate it to come out with the same sound as a clarinet. So yeah, so this is, I hope you'll find this interesting. Yes. Do you have any questions?
Yeah. I'm trying to simulate a bassoon, and I need conical tube elements. Do you have those in your library?
What is the element?
A conical, so that it has a slight difference of a slight radius, a different radius.
Yeah, we have let's see, we have a horn model. You have to simulate FDTD, but each segment is a little bit wider.
Yeah.
A little bit wider. Yeah. So I think it's already in the model, but we have a horn model coming up. If not, so
okay.
Thank you. Yeah, I remember you were asking about that.
Right.
Yeah, let's talk some more.
Talk some more. And are these models code generatable?
That's an interesting question. The short answer is yes. I've tried it, but it's not. You cannot simulate it in a variable time step. It has to be done in fixed time step. The fixed time step, you simulate using Simulink compiler, and it will run like 10 times faster also. So, yeah. So thank you. So let's. Sorry.
I do have a question.
Yes.
So basically, in order to use your library, I have to have the Simulink, right?
Yes. So in order to use the acoustic library, you need Simulink, you need Simscape, and since it's under acoustic audio toolbox, then audio toolbox is on top of signal processing toolbox and DSP system toolbox. So,
okay. So
which I think you said you have the suite, right? So you have everything.
Okay.
Yeah.
Okay. So I do have another question. So
Yes.
assume I use your library to model a certain type of loudspeaker. How can I compare? So the result, like from your library and the real loudspeaker.
Yeah, actually, I have done that. I will post my result out very soon. Meaning that first you need to measure the actual build, the actual library, the actual loudspeaker, measure the response, and then you compare with your simulation result. And I guess that's the short answer. You just have to compare it. There are a lot of subtleties. Like when you measure loudspeakers, there are a lot of.
Well, what do you measure? Is the input current and output as acoustic, like the
what aspect of it?
sound meter or something?
I want to say come back and show you actually how to measure loudspeaker nonlinearities as well. But there are a lot of different aspects of it. For example, if you want to measure I have a YouTube video out for measuring loudspeakers. So that includes like how do you measure for example, frequency response is easy. In Audio Toolbox, you have an impulse response measure, and that helps a lot. But anyway, sorry, our time is up. I would say let's have the next speaker. I think that's Jihad.
You tell me when I should stop. Highlight. Okay. Hi everyone. I'm based in Naples on the East Coast. I work on the development of Audio Toolbox, and I wanted to share with you some new functionality related to simulating the propagation of sound inside rooms. Okay, so here's the agenda, a brief introduction, and then there are two basic sections in this presentation. One that summarizes so-called geometric methods of simulating the propagation of sound in a room. I'll go through two basic methods there. And time permitting, I'll show wave-based methods, which are closer to the actual physics of sound propagation. And again, show you how you can model this in MATLAB and Audio Toolbox. All right. Why would you want to simulate the room acoustics? Well, what does this mean? There are many examples here. One simple example is, let's say you have a room, there's a sound source somewhere, a receiver somewhere, could be a listener, microphone. How do you figure out the impulse response that characterizes this room, which would include the line of sight if it exists and all the reflections and other effects of sound propagation? Other applications is finding the frequency response, analyzing the room modes, and so on. It's often cheaper than actually measuring the room response, which is tedious and probably expensive. And the applications are numerous: virtual reality, system design, architectural acoustics, testing algorithms. Often, if you want to test a new audio signal processing algorithm in a reverberant environment, a convenient way is to simulate or synthesize a bunch of realistic room responses and do it that way. Okay. As I said, there are two main families of methods here to analyze or simulate sound. One is geometric methods, which essentially treat sounds as rays or straight lines bouncing around the room and somehow being registered at the receiver. They are limited in the sense that they do not capture all the different physical characteristics of sound propagation, but they are often accurate enough, and they are relatively numerically inexpensive. For many situations, they're very agile. For other situations where you need more fidelity, You can use wave-based methods where the idea is to more directly solve the wave equation. So really model actual physics of sound propagation. Those methods capture all different characteristics of sound propagation by their nature, but they could be extremely expensive. So caution should be used here. I stole this slide from an external website that shows you the different methods under the two big families simulations. And time permitting, if Francis doesn't stop me, I'll show you a few of them. This gives you an idea of where the different techniques are good and relevant. Wave-based methods are accurate everywhere, but they are very expensive. So people typically use them at low frequencies, where geometric methods, such as ray tracing and image source, are not very accurate. So very often you'll find the hybrid approaches where you use these techniques together and combine them into one response to be as numerically accurate as possible. So with that being said, I'll focus first on some geometric methods with a very quick and high-level information about them to give you an idea. Let's start with the image source method, which you might have heard of. This might be the most classical, popular method of capturing sound propagation. It is the deterministic method, and it is useful for finding specular reflections between a source and a receiver. Imagine a source and a receiver somewhere in the room. There are a number of rays that bounce around, emanating from the transmitter, that find their way exactly at the receiver. The image source method is a geometric method that finds them. I'm highlighting the method here in a very simple example. You see the microphone and the speaker. The image source essentially finds or computes the image of the sound source. So this should be the speaker, actually. Just imagine this is the speaker. So we find the images with respect to all the boundaries, which would be the walls, the ceiling, possibly objects in the room. And by connecting the image to the receiver, you can determine what is the specular reflection that moves around the wall and exactly ends at the receiver. And you can do this for rays that bounce multiple times, so have multiple reflections on multiple walls by just doing this imaging multiple times, right? And as you can imagine, even for a very, very simple room, that's just an empty rectangular room, as the number of maximum reflections increases, the number of images explodes. And this becomes numerically untenable very fast. That's why people limit the number of reflections or the image source or something low, typically of the order of 5. 4 or 5 is where people stop. So this method is useful for finding the early strong reflections of the impulse response and not the reverberant tail of the impulse response. The good news in 25A with Audio Toolbox, you can use now function directly for this image source method, which is, relatively simple to do yourself for the simplest of rooms, rectangular room. But when things get more complicated for arbitrary shaped rooms with objects in them, doing all these images is complicated. And something I skipped is that there's a actual additional step to check that the image is actually valid, meaning that there's nothing between the source, the image, and the receiver, no obstacle. So it gets untenable. So what you can do now is just use a function in Audio Toolbox. I'm highlighting an example on how to do that. Some of you might be familiar with STL files. It's a popular file format to store shapes, rooms, objects, and so on. So what I'm doing here is I'm loading an STL holding a custom room, which now is an object in MATLAB that we can use. I'm defining where the transmitter and receivers are in this room with these points. And you can now call a new function called acoustic room response, which at the very high level takes the room, the model of the room, along with the transmitter and receiver coordinates. And you can control which algorithm and its parameters. Here I'm just using the source algorithm, which I just showed you. And I'm showing you output of this function, which is the impulse response ready for use. This could be consumed in MATLAB using filters and so on. There's a question.
Yeah, I don't have. I just want to make sure I understand this correctly. So basically, you have all those impulse response collected somewhere, then you save it. Then, as long as we can, we give you the geometry, I mean the dimension of the room, so then you can provide us the proper impulse response.
This is a simulation. The function simulates.
Simply the plot.
It finds all the image sources and it does the simulation to synthesize the impulse response. If that makes sense. We don't have pre-saved impulse responses that we retrieve. We actually compute it for you. Using the method I highlighted very simply for one reflection, we do it for tens and hundreds of images, and this is the result essentially. So as you trace each ray, depending on the distance traveled, this determines the delay at which you see it in the impulse response. And its power depends on how much attenuation it went through, which is both related to the distance it traveled and to the characteristic of the walls, how much sound is absorbed by each wall or ceiling. So that's all programmable into this function, and it gives you the answer, essentially, which is this IR.
Can you define on each walls the properties of the reflections?
Yes. So you can.
What is sampling rate? Sample rate that you have.
Yes, you can specify a custom sample rate. That will be the sampling rate of the.
For my receive, or like what does it mean?
This will be the sampling rate of the digital impulse response that's returned by this function. And to your question, yes, you can specify the absorption characteristics of all the objects.
Can you do curved boundaries?
Yes, yes. What MATLAB will do is it'll approximate the curve with a lot of triangles. But yes, you can do arbitrary shapes, which is the strength of this function. You don't have to worry about all this. It does it for you. So yeah, this answers actually the two questions. So it's great. Moving on to the other method that's more useful for the long reverberation tail, which the image source is really not good for. It's stochastic ray tracing is what we're using. Contrary to image source, this is probabilistic. Essentially, it works by shooting a large number of rays from your source and tracing them as they travel around the room. The difference with image source is this incorporates the effect of scattering, meaning whenever a ray hits a wall, there is a specular component that's a perfect reflection, but a certain amount of the sound is just scattered. And if the point at which the ray hits the wall can see the receiver, if there's no obstacle between them, a certain amount of that scattering energy is registered at the receiver. And by doing this for all the rays, you build the impulse response. I think I have a simple video here that kind of tries to do that for you. So we're tracing a ray as it goes around the room, and we're building a scattering histogram of the energy received at the receiver. Typically, this is done for multiple frequency bands because scattering characteristics of materials is frequency dependent. And then all these bands are combined to one response. Again, you can use the function, the same function, and specify stochastic ray tracing. Again, any room is supported. You can specify both absorption and scattering coefficients, and conveniently it returns the impulse response for you.
Which one is the scattering coefficient here?
Here, I didn't specify any, so it uses some default, which we'll document. But if you have your own specific scattering, you can specify it. I think we assume pretty rigid, smooth walls, so whatever scattering coefficient is there. But if you want
There's a wall property that you put into the geometry definition.
Correct. So there's a default for people who don't want to bother. But if you really want to specify all these numbers, you can. Okay, so we talked about that. The function has a lot of options that I'm showing to control how many rays you're shooting, to limit the number of maximum reflections for each ray. You can increase these numbers at the cost of extra computation. And you can combine these two methods, which is often done. Use image source for the early arrivals, ray tracing for the tail. Combine them together, and you get an impulse response that combines these two popular geometric methods into an impulse response. Again, you're in MATLAB, so you can take this impulse response, use the filter command or any of our filtering functions, do analysis on it, incorporate it into your simulation. So, all right. So,
does this method capture the resonance?
No, these methods are good for relatively high frequencies. And that depends on how big your environment is, because it's related to the wavelength. To capture resonant behavior, it's a good segue. You typically need to go to wave-based methods that more faithfully model the physics. And I do have a couple of examples here on wave-based methods. Just first, a very high-level summary of what we're doing here. Wave-based methods attempt to solve the wave equation, which is written up here for free space. And there are different methods to do that. Obviously, you can also solve the Helmholtz equation, which is very close, a derivation of the wave equation. One popular method is finite element method, which at a very high level divides your space into smaller areas and solves this partial differential equation for each of these areas, kind of a divide and conquer approach. Numerically extensive, typically. And I have an example here that I'm summarizing that will be available in Audio Toolbox soon that uses the partial differential equation toolbox, one of our products, as the FEM engine. This product already comes with an FEM engine, so I don't have to worry about implementing it, which is good. At the very high level, again, with the PDE toolbox functionality, you can create your room exactly like you do it for the ray tracing, but now you create a PDE system where the coefficients and the boundary conditions depend on what you're solving. Here, I'm showing an example for model analysis to find the modes of the room or the frequency at which the room resonates. And I'm plotting some results, axial, tangential, and oblique modes. Some of you might be familiar with them. They reflect the direction in which the waves are moving and what they're bouncing against. Almost done? Okay, so this is the last thing I'll show. You can also visualize the modes in 3D. And the nice thing is that this applies to any room, arbitrary shapes. It's a general solution that you can do. The last thing I'm going to show is another example we wrote using PDE Toolbox where we want to derive the frequency response in the room, assuming a transmitter is located somewhere. What I'm plotting is the frequency response for a certain plane. And I'm also plotting results compared to some theoretical values. There's some theory for simple rooms based on the green functions, things like that, combinations of all the eigen frequencies where you see a very nice match.
There are a few more slides I'd like to cover on finite difference time domain, FDTD. which is another wave-based numerical method for solving the wave equation in the time domain. The basic idea is to discretize the pressure function in both space and time, so only evaluate it at specific points in time and in XYZ domain using some kind of time and space step. We replace the derivatives from the wave equation with finite difference approximations. Here I'm using second order finite differences. And by setting the time step to a third of the spatial step and setting the X, Y, and Z steps equal, you get the pretty simple equation at the bottom describing the sound, propagation of sound in free space. The explanation of this magical factor 1/3 comes from theory where this number achieves stability. It is very simple to code up this equation in MATLAB, which I'm showing on the right-hand side in this subfunction free space. You can notice the matrix operations. P2, P1, and P3 are large matrices holding the pressure values at different time steps. And all these LL, MM, II indices are large vectors. So we're doing matrix operations in one shot. And I have a simulation stored that records the received pressure at a certain point, assuming a source located at a certain point in an empty room. Fast forwarding a little, you will see a point where the pulse, transmitted pulse, is received at the receiver. And since this is free space with no obstacles or reflections from walls, that's about all you receive. So this is a demonstration of FDTD in free space, which is not extremely interesting, but you can extend the same idea and integrate boundary conditions, which I'm not including here, but I have references for you to see where the math comes from, where you can also define what happens at the boundaries, which in our case, in an empty rectangular room, are the walls, the ceiling, and the floor. So let's run this simulation where I've chosen a high reflection coefficient on the all surfaces. What you see at the top is the transmitted pulse. The line of sight pulse is first received at the receiver place location. Then as we go forward in time, you'll start seeing reflection of all the surfaces. What I'm plotting, by the way, is a cross section, a horizontal plane in the room, just for convenience. And you see all kinds of effects now captured by this method, which are not captured by the geometric method, one of the strong points of this method, at the expense of more computations. You can see on your left the received signal with its reflected paths being formed. You can fast forward a little. Since there is a very high reflection coefficient, things take time to die off here, and you'll see some strong contributions in time. Okay, so here is the basic idea. I'd like to mention too that this method is parallelizable using GPUs. By its own nature, we do computations on a very large number of points in space that is independent. So doing it on GPUs can give you hundreds of orders of magnitude in speed up. MATLAB has a very convenient way of doing GPU computations. You just use the GPU array data type, which I'm highlighting in the small example, instead of the regular arrays. And that forces all computations to happen on your GPU. So that concludes my presentation. In summary, you now have access to geometric methods for sound simulation in rooms using Audio Toolbox in 25A, the function acoustic room response that integrates image and ray tracing methods. And MATLAB is also convenient for implementing wave-based simulations. We saw a couple of examples of FEM using the PTA toolbox, and I showed you code snippets that show you how to conveniently implement FDTD as well. Here are some references that capture the literature we based ourselves upon to do ray tracing, the image source, as well as FDTD and FEM. Thank you very much.
I think we're ready to kick things off for our second half here. So my name is Adam Cook. I'm an application engineering manager at MathWorks. Been there about 10 years focusing on signal processing, audio, and kind of a particular focus on getting things out of MathWorks tools and onto hardware. So working with our customers that want to take algorithms and applications and bring them into the real world. So as I mentioned, here to kind of talk about bringing things out of MathWorks tools into the real world with a particular focus on AI applications. So we recognize that a lot of AI applications start off in some other tools, other frameworks like PyTorch and Python. So we're going to focus on how we kind of integrate these tools with MATLAB and Simulink. So first off, just a little bit of basic context. What do we mean when we talk about AI for signal processing and AI for audio? So we're talking about bringing some sort of signal into an AI network. That network does something to it and produces an output. And in many cases, the purpose of an AI network might be to classify something. So this is when you're, say, trying to label a signal, like maybe you want to identify a sound source, like is it a cat meowing or a dog barking or whatever? We would call that a classifier. In other cases, the neural network is acting as a signal processing engine. So in other words, it's applying some sort of operation to the signal and just producing another signal as an output. This might be like the purpose of removing noise from speech or something like that. In other cases, you're using the network as a means to extract features, and we would call these embeddings. But one thing to keep in mind is that in many of these scenarios, the deep network isn't actually working directly on the raw audio or signal data. In a lot of these scenarios, there's some sort of pre-processing step in the middle. We would call this maybe a feature extraction, or in this case, when we're doing like a spectrogram, it's a conversion to like a time frequency representation of our signal. So what that means is if we're going to use an AI network and deploy it into the real world, we have to take into account any of this pre-processing. And of course, there's probably going to be some other stuff happening on the back end as well. So when we're talking about an AI application or AI system, it's not just about the network itself, it's about the full kind of signal flow from beginning to end. So of course, I'm sure most of you in the room are very familiar with spectrograms. This is just what we're talking about with regards to what is the actual signal processing operation that's going on. When we're taking a signal from the time domain into a time frequency representation, we have a sliding window that moves across, capturing FFTs every time that window slides forward. And then from that, we're able to build up this time frequency representation of our signal. And this is often what a lot of these networks are looking at. Right, so if a lot of these networks are being developed in some of these other frameworks, then why would we want to use MATLAB and Simulink in context with those other frameworks? So one of the reasons is what I just mentioned, is the network itself is just one piece of an overall system. So in many cases, if you're a signal processing engineer, you might really like working in MATLAB and appreciate all the other cool capabilities we have to offer for doing signal processing in MATLAB, and you want to just combine that with AI. And in other cases, you might actually want to take this system and deploy it into what we call a target, a hardware platform. You're maybe just rapid prototyping, or maybe you're even turning into like a product that you want to ship in the real world. Of course, you can also develop deep learning models in our tools, so you could do this whole workflow without involving PyTorch and TensorFlow. But that's not the focus of today's session. Today's session, I just want to show you how to take stuff that already exists in some of these other frameworks and bring it into MATLAB and Simulink. All right, so I'm going to talk about how to do the integration of the AI model first, and then we're just going to look at a few different interesting examples where we've integrated AI models from other frameworks and solve some interesting applications. So there's basically three main ways you can go about doing this. The first is what we call model conversion. So in this scenario, you're actually taking the model as it exists in one of those other frameworks and you're importing it into MATLAB. We have different functions that do that, and then you have a representation of that model in a MATLAB kind of data format. The other way of doing it is what we call co-execution. This is where you actually have a Python version of your model running side by side with MATLAB and Simulink. This has some benefits in that you don't have to go through and do any conversion and run into any potential hiccups along the way that might occur when you're doing that conversion step. But it has some downsides as well, which I'll talk about. These are some of the specific functions that exist for doing this conversion process. So we have two kind of domains or format-specific converters, one for TensorFlow, one for PyTorch. And this is kind of going along with what I was just saying, right? So it's not a perfect situation where every single model out there could be imported because this is a very quickly evolving, ecosystem of tools. So what we do is, we keep track of what's going on out there in these other tools and try to keep adding more and more support for different types of layers and things like that. But that moves very, very quickly. So what's supported today might not be supported tomorrow. So it's a very capable tool, but just being realistic, there's always going to be situations where it's not going to be perfect.
Does that mean that you have support for managing Python virtual environments like MATLAB or not?
Not really version environment. You mean different like versions of
virtual environments? Yes.
No, we don't do that. So for those situations where you might run into some of those challenges, that's where co-execution can be helpful because it just allows you to kind of bypass that process of importing. But it has some of its own downsides, which is that you have to make sure you have all the appropriate Python, PyTorch, TensorFlow libraries installed, and you have to do this data type conversion to get the data back and forth between the two different domains. But we are trying to make this process as easy as possible. So one of the newer things that we've introduced is just having a simple block in Simulink that you can drag in a PyTorch model directly into this block and execute it. And so that's something relatively new. I don't know exactly which release, either 24B or 25A. This capability came out. All right. But I wanted to focus a little bit more on the importing workflow because this is what's more interesting, particularly for the cases where you want to put something onto hardware. Because with the co-execution workflow, like we're showing here, you have to run Python side by side. So if you're deploying something to hardware, you're probably not, going to bare metal where you're going to have Python available. So in this scenario, when you do the import, if you look at the workflow here, you can do your complete modeling and simulation inside the MATLAB or Simulink environment with all that signal processing that we talked about for the pre-processing and the post-processing. There's an additional optional capability if you want to potentially compress your network to make it smaller and meet the requirements of your particular embedded hardware. And then finally, you can take advantage in this scenario of our code generation to actually deploy it onto the hardware. And not just generate C code, but we have these things that we call hardware support packages that take the generated C code, communicate with a particular compiler, and allow you to download directly to the target, kind of all within the MATLAB Simulink environment. So that allows you to do useful things like testing the performance and then verifying and validating your algorithm on a particular target.
Do you directly support TensorFlow Lite?
We do, actually. That's a great question. I didn't include that slide because I already had too many slides, but there's a couple ways you can directly support TensorFlow Lite. The method that we have in the version that's currently released today requires basically a TF Lite interpreter. So that interpreter runs inside of MATLAB, and also when you generate code for a target, like say a Raspberry Pi, that interpreter also runs on the Raspberry Pi. And then when you generate code, you're going to get the model running with that interpreter, but you're also going to get the generated code for everything around it, all the pre-processing and post-process. Great question. Thanks. So even if you're going through and doing this importing method, there's a handy tool in MATLAB called the Deep Network Designer. And even though the designer is right there in the name, it's still really helpful if you're designing elsewhere and then importing into, because it has these cool capabilities for visualizing your models. So you get like this nice kind of graph view here. And it also has some built-in things for exploring that compression step that I mentioned earlier, where you can analyze a network for compression capabilities. And we have a few different types of compression. One that we call pruning, one that we call projection. And it looks at all the different layers in your network. And it gives you like a check if that's eligible for doing a type of projection or pruning. And you get a little X if it's not eligible. And then it tells you what is kind of the maximum amount of potential pruning and projection available. Now, obviously, this doesn't tell you the effects of doing that level of compression on the accuracy of your model. So that's where the other capabilities for making this an iterative process become interesting, because you can kind of do the appropriate level of projection or compression for whatever problem you're trying to solve, because you don't want to compress your model down to 1% of its original size if you're going to lose 90% of its accuracy.
Why is softmax not compressible?
Why is softmax? I don't know why particular individual layers are and are not, but basically what we would do is we would go to the documentation page for these each of these two different compression methods, and it'll have a list of which layers are supported. But, good question. All right. So here's a specific example of using one of those import functions. In this case, it's import network from Onyx, but we also have import network from PyTorch and TensorFlow, and then doing that visualization inside of Deep Network Designer, what it actually looks like. All right, how are we doing on time, Francis? Okay. So now I just want to go through a few different interesting examples of AI systems, and we'll kind of look at a few different problems that we're solving with AI. So one is speech enhancement. So in this case, this was a model that existed in the community of open source, and there's a particular paper that was published here, and you can see this is a GAN approach. So there's a generator and a discriminator, and this network existed in PyTorch, and we went ahead and brought that into MATLAB. And in this particular case, we turned it into a function in our audio toolbox, where we kind of made it a very convenient, easy to use network, so that you can basically just give it some noisy speech input, and you can get cleaned up output. So are we sharing audio in the room, hopefully?
Yes.
It's easy to tell the depth of a well.
So that was our original clean signal. Here we added some noise.
It's easy to tell the depth of a well.
And then this is after going through the speech enhanced network.
It's easy to tell the depth of a well.
Obviously, it's noticeable, but it's significantly improved. Reduced amount of background noise. Another nice thing about when we package these things up is we try to give you these nice we call them convenience plots because they're very convenient. So here we're showing input, time domain, and spectrogram with all the noise here, and then output, time domain, and spectrogram as well. And then this is just, if we look at this network in the command window, this is an example of kind of what you would often see when you import a network. You see a lot of layers that match, precisely with their PyTorch equivalents. But sometimes you also have layers that are what we would call like a custom layer. This is where like the importing tool doesn't know exactly what to do. So what it does is it puts in a little placeholder, and it's up to the person doing the importing in that scenario to kind of author a MATLAB implementation of that layer. I didn't know it was going to open. Right. So another AI scenario we see quite often in some of our industries is the notion of detecting the health of a piece of machinery acoustically. And we've gotten a lot of leeway out of a particular data set out there that's consists of air compressor measurements. So this is like, the type of air compressor you'd find in a machine shop or something. There's a big data set out there where they recorded it in a healthy state, and they recorded it in a bunch of different faulty states. And the idea is to train a classification network to figure out, what specifically is wrong with this piece of machinery while it's running. So what's cool about doing this in Simulink, I recognize it's kind of small and hard to see, but we've got a bunch of different WAV files over here. This is what I was talking about earlier. We've got pre-processing and post-processing. So the feature extraction here, it's not doing a spectrogram, but it's doing a similar sort of thing where it's grabbing spectral features out of the time domain information, feeding it to the network, and then doing the post-processing is just kind of doing some averaging sort of things. And what's cool about simulating this in Simulink is you can get a nice visualization, streaming visualization in real time. And you can really understand, like, okay, how long is the network taking to make a decision? So this is a probability score. So it's kind of saying, like, okay, when I get to about 1 second, I'm very, very confident that it's a piston fault that is being detected. And then if you keep the simulation running and you change one of those inputs, you can see how long it takes before the system switches over to a different type of fault. We can see that the change took place right there.
Can you compile this down to run on a Raspberry?
Yeah, so exactly. So now what we can do, that we've got this running in Simulink, we can use one of those things I mentioned earlier called the hardware support package, and we can put it on different hardware platforms. So we've done this for a number of different platforms for this particular model. We have Raspberry Pi, and then this other one here is a ST Micro board with, so basically two different types of ARM processors. The ST Micro is a Cortex-M, the Raspberry Pi is a Cortex-A. And once we compile it down, we can measure the performance, which I'll show you in a minute. Before I show you that, I just want to mention we also applied model compression to this particular example. In this case, we used that projection method that I mentioned earlier. So we started off with a model with about greater than 85% accuracy. And the idea was to compress it without sacrificing, much of that accuracy. So you can kind of think of it as like having a knob where, there's going to be some certain sweet spot where you're going to be able to retain enough accuracy, but get enough compression to make it more efficient.
If you're not using spectrogram, what's your time frequency transform?
So it's still a FFT that's doing a conversion to frequency domain, but we're looking at other spectral features. We're not just using the whole spectrogram as an input.
And what does it take to make a hardware support package for these?
Like if you have your own hardware?
Yeah.
Good question. So it's call it a documented process, but not necessarily a trivial one. So you can do it, but usually I'd recommend, working with an application engineer at MathWorks to kind of help you through the process. It's easier, I would say, if your target is very similar to one that we've already done. Like if you have something that's maybe similar to a Raspberry Pi in that it's a Cortex-A and it's running Linux, embedded Linux or something like that, that would be pretty easy to do. Same thing for some of these Cortex-M targets that are pretty similar to ones we've already done. If it's something that's a bit more unique, it would be a little bit more challenging. But if you want to, feel free to follow up with me and I can send you some of the references and stuff like that. Yeah, so again, you're trying to find that sweet spot of different amounts of compression. So, you can take advantage of MATLAB and make this a loop and run it over different levels of learnable reduction. And you can see, you really start to get significant impact, obviously, as you get to the most extreme amounts of reduction. So again, every situation is going to be different, and this tool allows you to do that iterative process and figure it out. Yes.
Excuse me, when you say compression, do you mean specifically pruning or something else?
So this is a type of compression that we call projection. I'm not the expert on what's happening in this algorithm, but pruning is something that we would refer to as something different than projection. We have two different kinds.
Is it just projection to a lower dimension, maybe?
That's the gist of it. Yeah, but again, we can show you the doc pages with the details.
Okay.
Yeah. Okay. Right. So we went through when we did this projection. So there's a couple things you might want to take into account. So one is obviously the size of the network is going to affect the amount of memory you're using. So we looked at that, but also it's going to have an effect on the execution time. In this case, we get a distribution of execution time. I apologize, I used the wrong graphic here. This should have been the Raspberry Pi graphic because on a bare metal system, you really don't have any delta in execution time. It's going to always be the same. On a Raspberry Pi, you're running an operating system. You have other things going on. So you get a little bit more of a distribution of execution time. And then this is the other dimension I was mentioning, which is just the memory usage. We achieved about 26% improvement in flash, 6% in RAM, and 23% overall utilization for the CPU. And I don't remember exactly, I should have put the settings here in terms of like how much accuracy reduction there was, but it was less than 1%. It was very minimal. All right, and my very last one is a audio smart speaker example. So in this one, the hardware target was a Qualcomm Hexagon device, which is another package that we have hardware support package for. Now these are becoming very popular platforms in many different application areas. They used to be almost all exclusively in mobile, but now they're in automotive and other areas. And these are much more sophisticated than, say, like a Raspberry Pi or a Cortex-M, because they have many different accelerator co-processors available, including these things called neural processing units, which are accelerators designed specifically to run AI components. So when you have a big complicated model like you have here, which is a smart speaker, the AI component, which is the speech recognition, so it's waiting for its speech commands to turn on the music or turn the volume up or whatever. That part specifically is going to run on the eNPU, and the rest of it's just going to run on the regular Hexagon DSP part. And I think this is a really cool capability, because what we hear from most of the customers that are trying to do this sort of thing is that it's really hard to merge these two together using the standalone tools, because a lot of these big chip companies are putting out many different SDKs, and the SDK for the eNPU is completely different from the one for the rest of the DSPs. So it's not trivial to do these things with the discrete tools. So that's the idea with MATLAB and Simulink, is just trying to make this as easy as possible to merge these things together. I think I'm coming up on time here.
Okay.
Doing okay? All right. But just to show you real quickly what the workflow looks like when you're using this. So like this right here is going into the subsystem for the audio input for the smart speaker. So again, it looks very similar to all the other ones we've seen so far, right? We've got pre-processing, feature extraction. This one is using a spectrogram. You've got the network itself, and then you've got post-processing. Back a little bit too far. And then again, the goal here is to deploy this whole thing onto a hexagon. So when you have this hardware support package installed, it shows up as a dropdown up there. And then it's just a one button click. And what that button click is essentially doing is it's generating code specifically for that platform. And then it's also communicating with the Qualcomm tools. So it's compiling and then it's running. In this case, it's running on a simulator. And that is a benefit because you don't have to have a physical hardware board to understand, okay, how much CPU is my algorithm using on a hexagon. As long as you have the Qualcomm SDK, you have access to a simulator. And in this case, we run processor in the loop on the simulator. Even though it's called processor in the loop, it's really, I guess, simulator in the loop. And we can see we're using about 17%. And what's cool about, because we're generating the code for and taking advantage of that eNPU, is we got a huge performance boost because of that hardware accelerator. This is basically if you don't have a hardware accelerator, and it doesn't matter if you're using generated code or handwritten code, it would look pretty much like this without the hardware accelerator. This is when we turn on the hardware accelerator specifically for the AI. And then this is when we turn on all the other optimizations that we have for just the general DSP stuff like FFT and filters and things like that. All right, I'm done. So just bringing back to the conclusion. So again, the motivation here was to show you how like these tools can make it easier to integrate AI and signal processing systems into kind of one tool where you can simulate, debug, verify, and then eventually deploy onto target.
Okay, time go by so fast. This is the last presentation, and I was gonna just do a really quick one on this because I was expecting everyone's gonna run late, and yeah, there won't be enough time. So this is simple and it's going to be fun. And so basically, I wanted to first talk about sound quality, and especially I want to talk about is what is the measure that we do to say this sound is annoying. So I'm going to play a few sounds that's for the purpose of making you feel annoyed, and then we're going to find out which one you think that's most annoying, and then after that, we'll go through the calculations and see if we arrive at the same conclusion. All right, so just bear with me. This is the first one. Okay, so I guess we all know what that is. Yeah, so it's remember how you feel. Like actually, it's also depending on how loud it is. Like jet engine, if it gets any louder, you probably feel really annoyed then. But okay, so that was the jet engine. Now let's do the second one. All right, that feels like it will last forever. So that's the second one, that jackhammer. All right, now let's go to the third one. Yeah, that's because it's how annoying it's psychoacoustic, right? So I thought, something like that is fairly annoying to me. And since it's psychoacoustic, Then I thought, okay, now if that's the case, then this last one gotta be very annoying. Okay, so now we have 4 sounds. Now we have to rate. Okay, just raise your hand. Do you think the most annoying one is jet engine? Okay, jackhammer. Oh, wow, it's like most people, I think, will pick up this one. All right, about screaming sheep? A little bit, okay. And the last one, baby crying. Oh, you guys don't know at all. Okay, I guess you have high tolerance on baby crying. Okay, so
The worst one than baby crying is your 2 kids arguing with each other
yeah. For
and
me,
requiring your attention.
it's actually I shouldn't say, but I was gonna say it's my wife asking me to shut up. But okay, so let's see. So this is the agenda. We listen to some annoying sounds.
Again?
We're going to talk about some sound level, calibration and stuff, and proceed to talk about psychoacoustic measurement. And in the end, we'll draw a conclusion with a psychoacoustic annoyance index. So this is the waveform that you have listened to in time domain. We have a quick way of viewing this waveform. It's an audio viewer, and not only that you can view it, but you can click play and play it. So one point I want to make is, even if your recording is like lasting a few hours, you can still quickly view them because we're not loading all the samples onto the workspace in MATLAB. We're only loading the sample to display on the screen. So therefore, we're not loading every point. It's just according to how many points needs to be displayed. So it's a fairly good viewer.
How is it different to just plot?
Plot, you need to load every single point onto the workspace. So it would, if you have a long file for like a few hours, it would take up all your memory and space, right?
This works more like a DAW. I don't know if you've ever used like a DAW program like Audacity or something, but
it does some like level analysis beforehand.
Yeah, exactly. So when you're zoomed way out, you're kind of just looking at the envelope.
Okay.
Yeah, exactly. You're only looking at the
It takes windows of audio and just computes the min and max, and that's all.
So this is the picture for the screaming sheep. And this is baby crying. Okay, so now we're going to look at this SPL measure. And you see that a couple of things. First of all, the blue line is the maximum level. And the maximum level display, you can see that I'm trying to scale everything such that it doesn't clip. So everything's scaled like around 95, about 92, 93. And here you can see it's a little bit difficult, right? Just to let me call that everything is at the same level, because there's this peak to average ratio issue. Different sound has different ratio. So I can try, you see all these 3 signals, I try to scale it to the maximum of the same level and not clipping, but their mean value is a little bit different. And this, the first one, jet engine, I have it at the similar mean level, but then the max is not the same. So this is just one thing I want to point out. In displaying these plots, I'm using C weighing. And I also want to point out this is absolute. This is not psychoacoustic. So this is just directly measuring the level of the sound. Now, in terms of psychoacoustic, we have all these 6 measures. There's the loudness, sharpness, roughness, sense of fluctuation, speech intelligibility, and tone, pure tone sensitivity. And some of these measures I'm going to use later on, like loudness, sharpness, roughness. These I will use later on to calculate the annoyance index. Now, this particular one, speech intelligibility, I want to point out because there's these two functions, visco and story. That's really good. That I really like. So bottom line is, for visco, it's published by Google, and you send a file in, and you can get a MOS score back, a mean opinion score. So that is really interesting. So when I was working like 6-7 years ago, we have for example noise suppression scheme made, and we have to hire like 100 people in, everyone listen to it and give us a rating. And so that rating is essentially the opinion score. And then sometimes it's hard to get. And now we have these automated measures that we can immediately get a feedback. And it's really, really effective to tune your system. There are other ones out there like PasQ or Polka. Those are, it is popular, but it requires licensing and all that. But now this one is available in MATLAB. So I see that this is going to be very popular. Okay, so now back to our fun game here. So this is a compare of the 4 sound within loudness. Loudness is actually psychoacoustic, so you can have a sense that it's actually related to your perception. And I can look at it. I see that there are certain sound that has a higher level. You can see that the yellow one is higher level. And for this one, maybe it's a jet engine seems hard. But I don't know if we cannot just use loudness and decide that that's the most annoying sound, right? So it's a possible candidate is maybe this one is loudness is higher. And that's all I can say. The next one is the acoustic fluctuation string. So this is measured when there is a slow modulation. And so let's look at the result. This one here, fluctuation string, we can see that the jackhammer has obviously, it seems to have a higher level or higher fluctuation. So maybe if the annoyance is related more to fluctuations, then maybe the jackhammer is the winner. And we have a measure of roughness. Roughness is just kind of like the modulation earlier, but this one is too fast to perceive individual intensity. And let's look at it here. Comparing to the all 4, jackhammer again, that seems to have a little bit more intense than the other 3. There is a prominence ratio. This one is just comparing through, including the critical bands. And this one is interesting. You can see that the jet engine actually has a little bit more intensity. So with all this, now we come to the last part. This is the psychoacoustic annoyance equation. And at the end, I will give you the reference. That's according to a paper. But from this equation, you see that to calculate the annoyance level, it requires the acoustic sharpness measure. It requires the fluctuation, and it also requires the roughness. With all these values, you lump it back into the equation, and then you can calculate a PA value out. So now we have already done all these measures earlier. So now we have just like plug all the numbers in, put in this equation, and find out what the sound is really the most annoying. So this is the end. So let's say drum roll. And the winner is jackhammer. So indeed, so most of our audience got it right. You raise your hand saying that indeed is the most annoying. So it is quite obvious the number is higher than the rest. So Great. Okay, so time go by so fast. That concludes our meeting today.
Thank you very much.
I hope to see you.